You just look at this simpler version of the equation. So y is equal to 0 is definitely one of the solutions. You want to have y to 8 is equal to 1, and y is a real number. So the only two chances for this to happen is y equals -1 or 1. And that's it. It's up to you. Okay? The point is, we're not in the pre-calculus course. I will give you all kinds of different equations to solve. Using substitution is a very useful. We always try that. But there are some cases you can solve the equation easily, okay, using different methods, depending on what equations you're getting. You know what I mean? You might get rational functions. You might get exponential or logarithm functions. Solving them requires different skills, different tools. But I'm not done yet, right? Like I said, as long as I get the y value, I can easily get the x value as well. So x is equal to minus y cubed. So it's going to be 0 and 1 and minus 1. All right? 0, 1,
yeah.
minus 1. Or minus 1 and 1.
Yeah.
Minus 1 and 1. To be careful, I should be minus 1 and 1. And when I'm getting the point, I need pairs of numbers. Here you have to be quite cautious here. When I'm pairing these values together, I'm getting a pair of numbers. For instance, y is equal to 0. Can I pair all the other numbers with 0 here?
No.
Can I do that? What I'm saying here is, if I'm choosing y value to be 0, can I get 3 pairs coming from the 3 different values of x? And then if I choose the 1 as my y value, can I still get 3 pairs coming from these 3 different values of x? So this is the pretty much only thing you have to take care of. So let's get back to our fundamentals. To be a critical point, I have to require both of these two equations to vanish. Right? Both of these two equations are valid, which means when I solve these two equations, I get the solution of y. Simultaneously, I also have the relation between x and y. Am I right? So I solve for y, I get 3 values, but this relation between x and y should be always true. Right? Because this is coming from one of the equations. Both of these equations are valid. Means this equation has to be always there. Which means if I pick my y value, my x value has to be coming from that equation. You know what I mean? I cannot choose x freely coming from here anymore. So I have to have 0 minus y cubed, 1 minus y cubed, and minus 1 minus y cubed. So these are the only 3 critical points. Okay? So remember, you're solving a system of 2 equations. You have to keep the relation between x and y all the time. Right? In the end, you eliminate one of the equations to solve for one of the variables. But the other variable is also connected to this one by the 2 equations, even if you solve by eliminating one of the equations already. So these 3 are 3 independent variables. These 3 are 3 critical points. Okay, questions? Okay, so next I want to go back and translate the second order derivative into multivariable case. So the second order derivative test is, I would say, one of the most important applications for partial derivatives. Okay, so now we have 4 second order derivatives. Right? So if you still remember, when I introduced the second order derivative, I wrote them into this 2x2 matrix. Okay, so this is the second order derivative taking with respect to x first and x second. This is x first, y in the second time. This is y first and x in the second time. This is y and y. Okay, and also we learned this very interesting property about second order derivative, which means these 2 are always equal. At least within this class, these 2 are always equal. All the functions we're discussing are nice functions. So these two are equal. So this matrix is a 2 by 2 symmetric matrix. And in a lot of tests, this is called a hash matrix. Okay, so it is denoted as HF of X1. So it is a matrix consisting of all the second order derivatives. Okay? And the second order derivative test involves the determinant of this hash matrix. So if I have a D of F in the textbook, it's just a D of AB. And so D of AB is equal to the determinant of this hash matrix at AB. So AB is just the point. So if I take the second order derivatives, putting into this 2 by 2 matrix form, I'm just taking the determinant of this matrix. So it is essentially equal to Fxx Fyy minus Fxy times Fyx. But we know these two are equal. So essentially it is equal to Fxx Fyy minus Fxy squared. Okay? And then everything is evaluated at the point AB. Okay? So this is the determinant of the hash matrix. Okay? In a single variable case, if you remember right here, we have a single second order derivative. It is greater than 0, then we know it is local minimum. If it is less than 0, we know it is local maximum. For second order derivative test, we have two variables. We have to put all the second order derivatives together and study the property of this matrix. So the test is that if D of AB is greater than 0 and Fxx is greater than 0, then AB is a local minimum. Exactly. So if DAB is greater than 0 and Fxx is less than 0, then AB is a local maximum. Okay? If DAB is less than 0, then AB is a saddle point. And last is if DAB vanishes, then it is inconclusive. So basically there are 1, 2, 3, 4 different chances, different cases. Okay? So this is going to be our second order derivative test, together with the first order vanishing giving you critical points. So putting them together, this is how you find all the extreme values for a function with two independent variables. Okay? Do you still remember the picture of a saddle point? Yes. You still remember the saddle point. So I have one local minimum at a point if I follow one curve on the surface, and then if I follow the other direction, I'm getting a local maximum, right, on the surface. So this is what a saddle point looks like locally. So in some directions, you pass through this point, you achieve the minimum value at this point. In some directions, you pass through this point, you're achieving the maximum. Okay? So in the second order derivative test, if you have two independent variables, this first case is saying at this point AB, if it is a critical point, and we want to classify it as a local maximum or local minimum. If both of these two conditions are true, it is a local minimum. So you can pass through this point in arbitrary direction. It's always going to achieve the minimum value. You know what I mean? It's always going to achieve the minimum value. So at this base point, if AB is a critical point and these two conditions are true, no matter which direction you pass through this point, the function value will always achieve a local maximum. Okay? Whereas for saddle point, whether it will be local maximum or local minimum depends on which direction you pass through this point. Are you with me? So this is what we mean by the three different cases. And when the determinant of the hash matrix is equal to 0, is inconclusive. Strictly speaking, it is only inconclusive from a second-order derivative test. You can still have other tools to determine whether it is maximum or minimum. But it's just this matrix will not tell you anything. Okay? So think about what do you need to do. So if first-order derivative test tells me this is the critical point, second-order derivative test, the second-order derivative is also equal to 0, which means it's inconclusive by computing the second-order derivative. What do you do? Right, can guess? So what I'm asking, what if I still want to see whether it is a local maximum or local minimum, even I cannot tell it from the second-order derivative?
You gotta test each critical point by itself, so I have to plug it back to the function, see if it's positive on the left side of it, and then if it's negative on the right.
You can always compare the function values, so I agree with you. However, a much easier way to do is I can compute the third-order derivative. You can compute the higher-order derivative to tell whether it is local maximum or local minimum. If the first-order derivative vanishes, second-order derivative also vanishes. You have to go higher. Okay.
That's only talking about XX, right?
Yeah.
Second derivative with
But in that case, it's even more complicated because if you're taking third-order derivative, you're going to have
12.
how many are there?
8.
You're going to have 8 different ones, so it's going to be more complicated. But in any case, we are pretty much bounded by second-order derivatives, so you don't need to worry about that case. So I want to quickly practice a couple of points. I want to make one big remark here. The second-order derivative test is only working for critical points. With me, so I have to find the critical points in the very beginning in order to even use the second-order derivative test to classify these critical points. Okay, so I have to find the critical points by taking the first-order derivative vanishes. So fxy is equal to x squared minus 4y squared plus 1 is equal to 0. Oh, no, just the function. Okay? So a typical question will be find all the critical points and classify. Okay? By classify, we mean use second-order derivative test. That's all. Okay? So classify this point is whether the function will achieve maximum value or local minimum value, or it is a saddle point, or it is inconclusive. Okay? So you definitely have to remember the second-order derivative test, all the criteria here. Okay? So now there are not so many things to remember throughout the class. This thing is basically just a natural. Okay, so the first step is to find the critical point. Right? So what do? Fx is equal to 2x is equal to 0. Fy is minus 8y is equal to 0. So I have one and only one critical point at the origin, 0 and 0. Okay. Still, keep in mind the critical point is a point in R2, so we're supposed to have a pair of numbers right here. Okay. And then I needed to compute the second-order derivatives for this function. Okay. So the second-order derivatives, if you want to use this formula directly, you can just compute the second-order derivatives. And what I prefer, I want to write the matrix. So fxx is going to be 2. Fxy is equal to 0. Fyx is also equal to 0. And fyy is minus 8. So this is the matrix. If I compute the determinant, it's minus 16, which means write down the formula explicitly. It's d of 0, 0 is equal to fxx, fyy minus fxy squared. All you value at this given point is equal to minus 16, which is less than 0. Okay? So as long as the determinant is less than 0, you're already done. You're already done. So basically this says 0, 0 is a saddle point. Okay? So if the determinant is equal to 0, you're immediately done as well. It's inconclusive. The only complicated version is coming from when the determinant is greater than 0, then you need to look at the very first entry, whether it is positive or negative. Okay? Whether it is positive or negative. Okay, so I want to mention one extra stuff you don't have to remember here. I have these 4 different criteria to tell actually a matrix. This matrix is symmetric. If you still remember, have you taken linear algebra before? Some of you probably did. So if you have if you have one 2 by 2 matrix and it is symmetric, you can find both of the 2 eigenvalues to be real. Okay, you can actually find 2 eigenvalues. This case is saying if the determinant is less than 0, then you have one positive eigenvalue, one negative eigenvalue. If you have these 2 cases, you have 2 eigenvalues of the same sign. This is saying the 2 eigenvalues are both positive. This is saying both eigenvalues are negative. Okay, so determined by whether you have 2 positive eigenvalues, 2 negative eigenvalues, or 1 positive, 1 negative, the convexity property or the local maximum or local minimum are essentially determined by the eigenvalues. Okay, so I will give you one word if you want to look it up. So eigenvalues. Okay, so if you prefer to use it by the method of eigenvalues to determine its convexity or concavity, it's actually much more friendly than remembering all the criteria. However, within this class, you don't have to do that. Okay. So this is just a small taste of the second order derivative test. Next, we can get one easy question as well and see we can up our game. So I have a function fxy is equal to x to 4 plus y to 4 minus 4x minus 4y plus 1. Okay? So still the question is to find and classify all the critical points. So finding a critical point is still a matter of solving a system of 2 equations. All right? You have 2 first order derivatives, so it's always solving 2 equations. So fx is equal to 4x cubed minus 4. This is equal to 0. So fy is equal to 4